and let's move on to the last presentation in this session. And our third speaker is GBeaunee. He is a researcher at INRA, France, and today he will talk about reconstructing neighborhood networks and impact on the spread of a pathogen in animal populations. The floor is yours.
Thanks, Stefan. Do you see my screen?
Yes, you can see it.
Thanks. So thanks for giving me the opportunity to present our work today. And so I'm gonna talk about how to reconstruct neighborhood network and the impact on the spread of pathogen in animal population. So so as we know, pathogen the spread between farms choose different route. This is always possible through animal movement, and this will lead to long distance spread. And the structure of this is a cattle trade network. And this is also possible and by direct or indirect contact that I will call over the fence, that are transmission route on short distances. And this is what I will rely on neighborhood contact network in the next slide. So we have these two kind of structure for transmission of the pathogens. And we have different kind of information available. For cattle trade network, most of the time you have comprehensive data that provide an accurate information of the structure on which pathogen could spread. So this kind of data are available in more and more countries in a very accurate way. But for neighborhood contact networks, the problem is very different. In France, this is kind of anonymized data for the pasture network. So we don't know most of the time. We are not allowed to know which pasture belongs to which farmers. So we have to reconstruct, to rebuild this network based on land cover data. So this kind of data. So the question is, how does the reconstruction of the neighborhood contact network will be able to do, will influence the prediction of the spread of pathogens. So if, for example, you have just the location of your farms and you have a system on which you will have transmission on something like a medium distances, like few kilometers, for example. So easier way to rebuild the contact network will be to just use a buffer between the farms. But if you're considering some mechanisms of spreading at very small scale, for example, few meters, that is really over the fence. So you will not be able to do that. So to try to answer this question, we'll focus on one particular study area. So this is part of France in the southwest, for which we have access to livestock trade movement. And we also have, luckily, for just particularly for this area, to comprehensive data that allow us to rebuild the actual neighborhood contact network. Because we know for this area, for each pasture to whom it belongs to. So a brief overview of the method we used is that first we reconstruct the kind of epidemiological unit and then build a neighborhood network. Then we try to analyze the network to network analysis very simply. And then we assess the accuracy of the different network we build through dynamic modeling of the spread of pathogen. So first, the reconstruction of epidemiological unit, because here we're not focused on farms, but on maybe possibly several farms and a set of parcels, because maybe some farms can share some parcels for pasture purposes. So this is the definition of our focus node, so the epidemiological unit, and in order to assign the land parcel to each epidemiological unit, we will use 4 different ways to try to do that. First, based on the location, but we don't know the exact location for the farms, but we have access to the address of the farm. So address could be the administrative address, so not really accurate, but this is kind of information. And for these, we do some geocoding on the address using 2 kinds of different ways. One is EthaLab, that is a specific tool for France, and with Google, the tool from Google. And there is 2 other ways that are based on the administrative unit, because we know for each farm to which administrative unit it belongs to. And so we could try to do random matching or to matching by size. The idea is that if you're big farms, you will need more pasture area, for example. So during that, we were able to build some neighborhood contact network. So as I said, the node corresponds to epidemiological unit, and a link between epidemiological unit corresponds to a proximity between 2 parcels of 2 epidemiological units. So we build some buffer with different size. So one is 3 meters and another is 100 meters. So the idea is that you have something that is really over the fence, and for the 100 meter is that you consider different mechanisms that could lead to the spread of the pathogen to medium distances. So I will not show the result, but just briefly, we do some network analysis using static indicators on the different network we build. So for the one geocoding with the EthaLab tool, we obtained something that was pretty similar from the real network. Using the tool from Google, we underestimate most of the indicators. Using the random matching, we obtained similar network that was pretty similar based on the indicator, the value of the indicator, but on average, because as there is a lot of randomness, this is random, you are able to build different network, and each time you relaunch the reconstruction, you will obtain something different. If you take just one iteration, it will be a little bit different from the real network, but on average, this is similar. And if you use the first way, the size, you will overestimate almost all the indicators. But so this is some kind of information, but this is based on static indicator, and we know that pathogen will spread through a neighborhood network, but also with the trade network, and the trade network is temporal. So it was important for us to try to assess the accuracy of the different network, the relevance of the way to build the network based on some simulation of the spread of pathogen, taking into account the temporal aspect. So for this, we build a simple model that is stochastic for the infection, but deterministic for the other transition. So we consider 2 main transmission routes, I said, so through the neighborhood contact or purchase of an infected animal. And we designed the experiment to allow varying the importance of one transmission route relative to the other. So, and this for a fixed value of R0. And we consider two types of diseases. One we'll consider that is highly contagious infections that spread fast, and more slowly transmitted diseases. And the idea is we could ask if the impact of the reconstruction is the same depending on the pathogen considered, because pathogens are very different, and maybe reconstructing the network in one way or another will don't have an impact for one pathogen, but a lot of impact for another one. So very briefly, the dynamic mechanistic model we built is like that. So we have three kinds of nodes. We have the farm that are the epidemiological unit. We have assembly center and markets that correspond to node in which animals go through and spend 1 or 3 days and then are sent to epidemiological units. So we also consider the rest of the world in the model, considering that risky trade movement could come from outside of the population considered the study area. And so here we have just a very simple schematic to explain how we consider the transition for the farm. So the transition from susceptible to infected is stochastic, and then all the other transition are deterministic, and we consider just a mean level of prevalence during the duration of the infection. So for the simulation, so we focus on the study area I just showed before, and so we used data on 2014 because this is the year for which we have the pasture network data, and so to be able to do simulation on a longer period, we loop on the movement data. The population considered was initially free of the pathogen, and within a zone that was also free. As I said, so we consider two duration for the infection, so 8 weeks or 52 weeks, and two type of introduction, by movement or random, because you could consider that the infection will come from a risky movement because we are in a free area. But it was also, for us, we consider it was interesting to consider another kind of introduction that was more random. And so we consider different value for the ratio that range from 0 to 5, considering the importance to the pasture network over the trade network. So this leads to a lot of scenarios, 360 scenarios, and I will now show some results of that. So first, we're interested to the epidemic size. So here we have a figure showing the proportion of infected nodes for a buffer of 3 meters, introduction by movement. So there is a probability to introduce infection that is proportional to the number of animal purchased by each epidemiological unit. And so this is the result for the fast epidemic, but we obtain something very similar for the slow one. And what we observe is that the network you rebuild using EtherLab tool is the one that perform the best. And for example, for the one using the tool from Google, we underestimate and from using the network built on the size, we overestimate. So here is just a big picture to resume all the results for different scenarios. So just the idea is to see that most of the time we underestimate or overestimate, and the mean absolute deviation is 0.23. So when this is red, this is because we underestimate, and blue because we overestimate. I forgot to say it. And the intensity of color corresponds to how we over or underestimate. So this is when we are the scale of the node, but we were interested also to see what happens if we go on a more aggregated scale, so the admin units. And what we see is that there is less deviation in that is half the other one. Yes, speed up. Yes. Yeah. So just to speak about another kind of output is that the probability of being infected, and also here we look at that at the scale of the admissive unit, because this is the natural unit of aggregation, and we are able to assess only at this scale. We are able just at this scale to do a comparison between the admissive units. So what we show is a map, and here we have an example for one scenario and the four network, rebuild network. So more this is blue, if this is green, this is that we have something similar to real. If this is blue, we underestimated. If this is yellow, we overestimated. And what you see, for example, is that for ETL and Google, it is pretty similar to the real network, but for the random network, this is underestimated and overestimated for the network using size. But this is behaviors that are not really easily predictable. So I will just pass this a little very quickly, but this is, for example, what we obtained for an introduction using random. And this is what we have when we use an introduction based on the movement. So we obtain very different things. So it's very difficult to predict. So just to conclude, the key message is that there is importance of having access to accurate data. Bridging realistic network of neighborhood contact is key point to accurate prediction of pathogen spread. If you consider mechanisms of the short distances, there is significant risk to underestimating or overestimating the dynamic of infection by using an irrelevant method to rebuild the network. And accurate geocoding seems the most interesting approach for us using the ETALAB tool, specifically for France. And what we see is that it is preferable to use an aggregate scale to a fan scale for simulation output, to have a higher probability to be close to the true dynamics. Thank you for your attention, and sorry to be a little bit long.
Thank you, Gael, for a very, very interesting talk. Do we have any questions in the audience? I cannot see anything in the chat. And I don't see any hands up. So I have yeah, Elisabetta, please.
Yes, thank you, Gael. So one quick question was about the efficacy in terms of computational efficacy. Is there a difference between the options you had, so based on ETALAB or Google or etc.? Because are they more or less computationally expensive? Because this might be one of the criteria to be accounted for.
Yeah, for sure. Using geocoding is more costly because you have to do the geocoding of the address of the farms, and then you have to rebuild. If, for example, you use random allocation, you just have to use the algorithm to assigning the parcel to the epidemiological unit. So yes.
Okay, thanks.
But apparently, yeah, using random allocation is not really the best one.
No, but it depends also on the question and the
Yeah,
error
yeah,
you
yeah.
might you might accept. So
Yeah, and
in some circumstances, maybe it's not so bad to take something simple, to be aware of the fact that you can have an error, but if if it's not too large and the way to rebuild is quite simple and quick, maybe it's a bit a trade-off. But
yeah, for sure. If you're considering mechanisms that occurred at the range of the kilometer, for example, something like 3, 4, something on airborne diseases. So maybe it will be sufficient to use random allocation. But yeah.
Okay. Thank you.
Are you planning to do, now you are in the southwest of France, if I understood it correct. Do you plan to try this in another area or in another year?
Yeah, so the idea was to try to define the best way to rebuild the neighborhood contact network. And so we're only able to assess which method is the best using this area because we have access to the comprehensive data. But the idea is to now we have some clue the best method to use that for other regions in France and try to rebuild some neighborhood contact networks that are the best as possible.
Do you have the code available to do this kind of work? Would it be possible to apply this in another country, for example?
Yeah, for sure. So we will write an article about that. So and we plan to release the code and give an access to the code to do that. So just to and you will be able to just apply this to another area if you have the same kind of data. But yeah.
Thank you. There is a question in the, yes, okay, you just answered that. There was a question about, do you have a paper on this? And yes. Thank you. Any other questions in the audience? Yes, Colin Birch.
Sorry, but slow to get the microphone on. Very interesting presentation. At the end, you referred to difference between aggregate scales and bind scales for outputs from the model. I wasn't quite clear what you meant by that. Can you explain that a bit more?
Yeah, it's that what we're doing is that we are doing some simulation at the node scale. So in the model, what the epidemiological unit we consider are we could say the farms. And what we see is that if you're focusing your results on the node, so the scale on which you are doing the simulation, what we observe is that you will be less accurate than if you consider an aggregated scale. But the aggregated scale is just on the result, is not for the simulation, because for each epidemiological unit in which to which administrative unit it belongs to. So you are able to aggregate all the results to this scale. And what we see is that using this scale, so the aggregated scale, you will have predictions that will be close to the one done with the real network.
Okay, I see. So that could be a way around the data confidentiality issues.
Yeah, also, yeah. This is another argument to use Z scale. So yeah, because most of the time you are not allowed to give result as a farm scale because this is simulation. But so some people could interpret that, and yeah.
So potentially you could get access to very granular data on a secure data service, but present your outputs at the aggregate scale.
Yeah, but for sure. But the point here was that just using one scale or another, a filer or cross scale, you see that the accuracy of your prediction are not the same. Because finally, I think it also depends on the mechanisms you consider for the spread. If you consider mechanisms that occurs at very large distance, maybe it will not be the same. But yeah.
Thank you.
Okay, thank you, Gael, and thanks again to all three presenters in this session for very nice talks.